So spend a few moments looking at this heating curve. Try to determine what a good description of the material in the container would be at each of the question marked locations. Note that some locations are heating or becoming warmer, and other locations are transitioning from one phase to another. For example, question mark 1 is in the region where a solid is being heated, so the material must still be solid, and it's a relatively cold solid because notice it could still get quite a bit hotter before it began to melt. So we could say for question mark 1 that this is all solid and it's a relatively cold solid. So what about the rest of the question marks? Are they solid, liquid, gas, or a mixture of those? Are they on the colder end of that region or on the hotter end of that region? And is the temperature still changing where those question marks are, or is the temperature remaining constant? Sometimes people are a little bit confused that there's a heating slope above gas, but gases can get hotter and hotter and hotter too. They're always hotter than the liquid phase. So what determines specific melting and boiling points? It's going to be a combination of the mass of the individual particles. That's essentially a need for a specific amount of kinetic energy to be moving enough to be in that phase, and the strength of the intermolecular forces of attraction. That's going to require additional energy to disrupt these attractive forces. So both these factors, kinetic energy, essentially mass here, and intermolecular forces, are going to influence melting and boiling points. Now, it turns out that boiling points are also influenced by the atmospheric pressure surrounding the substance, since becoming a gas involves escaping into the surrounding atmosphere. We'll look more closely at that in a little bit. Mass matters the most. So for substances with only very weak attractive forces between the molecules, mass is the biggest influence on melting and boiling points. Heavier molecules are going to move more slowly than lighter molecules at any given temperature. Remember, temperature is a measure of the average kinetic energy of the particles of the substance. Lighter molecules tend to have lower melting and boiling points. This is going to be generally true unless IMFs are a big factor. IMFs also matter. For substances with strong attractive forces between molecules, IMFs are going to exert a large influence on the melting and boiling points. They tend to have raised melting and boiling points if IMFs are strong. Usually, we find that we should look at mass first and then IMFs when trying to compare or predict melting and boiling points. Let's look more closely at boiling point. We're going to focus on liquids and the change from liquid to gas because we see the biggest influence of IMFs here, because in the transition from liquid to gas, the IMFs between the molecules of the substance are completely removed. We're going to look at boiling point, a bit at vapor pressure, and then we've already tried to make some connections to viscosity and surface tension, and many of the labs you're doing will make connections to solubility. Boiling. One definition of boiling is when gas bubbles form throughout the liquid. They rise to the surface, break, and release vapor. This is a whole substance event. It's basically what cooks call a rolling boil. It means that all the molecules of the substance are ready to become gas. To boil, the molecules have to begin to move faster and faster, and the IMFs between the molecules have to break. So we would expect heavier molecules to have higher boiling points. But remember, IMFs can stick molecules to one another, and that can make even a very lightweight molecule have a higher boiling point because of the energy needed to break those IMFs. So the first definition we have for boiling point is the temperature at which vapor bubbles form throughout the liquid. At the boiling point, the entire liquid has enough energy for the molecules to enter the gas phase. This temperature will vary with the surrounding atmospheric pressure. So, at this point, vapor bubbles are forming throughout the liquid. The change to the gas phase is not just at the surface. The liquid vaporizes. Mass always influences boiling points. It's the first consideration. When trying to make a prediction or comparison of boiling points, always take mass into account first. Heavier substances require higher temperatures to get the particles moving fast enough to change phase. If there's very weak attractive forces between the particles, mass alone will account for differences in boiling points. But remember, attractive forces also influence boiling points. They're the next consideration. First mass, then IMFs. Substances with strong forces of attraction between the molecules require higher temperatures to break or weaken these attractions, although remember the molecules themselves are not decomposing. Let's take a look at some benzene boiling. Don't pay any attention to the temperature. The temperature is just there for a completely different thing. What you want to note here is that all of a sudden the IMFs lose out to kinetic energy and the entire substance becomes the gas phase. And then as they let it cool back down, all of a sudden the IMFs can take control again. Let's see.
As the temperature rises, the liquid meniscus flattens. This flattening is due to the increased energy of the benzene molecules. The forces due to increased molecular movement are beginning to overcome the attractive molecular forces at the surface. At the edges of the vial near the liquid surface, the benzene can be seen boiling. When the critical point is reached, the meniscus disappears and only diffraction irregularities are present due to temperature gradients. Here, the forces due to molecular movement overcome the surface tension and the separation between liquid and vapor disappears. Above the critical temperature, only the gaseous phase exists. A gas above the critical temperature cannot be condensed into a liquid since the molecular attractive forces are dominated by the rapid molecular motion. As the temperature decreases, the meniscus reappears at the critical temperature. The molecules in the gas move more slowly, allowing the attractive forces between the molecules to become dominant. At this point, separate liquid and vapor phases form.
Now let's make some predictions using the competing factors of kinetic energy and IMF. Which of these two compounds should have the higher boiling point, C sub 3H sub 8 or C sub 8H sub 18? Complete structural formulas have been given. Think about mass and think about IMFs. Remember, start with mass. One of these molecules is much more massive than the other. Much more massive. That molecule, that substance, should have a higher boiling point. Mass matters most in this case, and we've really already solved the problem. The heavier molecule will have the higher boiling point. But we could also come at it from a IMF's angle. London forces are always stronger between larger molecules. So since C8H18 is larger and heavier, the London forces of attraction are stronger, and the ion molecules are more difficult to move into the gas phase. They're both nonpolar, and so London forces are the only IMF attracting the molecules to one another. And you kind of actually already knew this one if you recognized the compounds. C3H8 is propane or country gas. It's a gas already at room temperature. They have to liquefy it to bring it out and put it in the tanks. C8H18, octane, is a major component of gasoline. It's still a liquid at room temperature. In other words, it has not yet reached its boiling point. It has a higher boiling point than propane. Let's try this one. Which compound would be predicted to have the higher boiling point, A or B? Remember, mass first, then IMFs. Their mass is about the same, so we need to look deeper at IMF differences. Compound A is a hydrocarbon. It's nonpolar, so it only has London forces possible. Compound B is an alcohol. See the OH group? It's polar and hydrogen bonding capable, so it can do dipole-dipole and London forces in addition to the very powerful hydrogen bonding. Substance B has much stronger IMFs between its molecules, so substance A should boil easily and substance B should boil with more difficulty. Their mass is about the same, but B has stronger IMFs. So we predict that B will have a higher boiling point, and in fact, that compound has a much higher boiling point than compound A. Let's try this one. Try to explain why compound C would be expected to have a much lower boiling point than compound D. Mass is identical here, not just about the same, but identical. These are skeletal isomers of each other. They have exactly the same molecular formula. So it can't be mass that matters. That means we have to look deeper at IMFs. When we look at the IMFs, compound C and D are both polar, so they can both do dipole-dipole. But D has much stronger IMFs than compound C. Note that D has the OH group. It can engage in hydrogen bonding. C cannot. So the weaker IMFs in substance C to boil more easily. So now let's look at the halogens. Iodine and chlorine are both nonpolar, as are all the halogens. But iodine is found in nature as a solid, and chlorine is already a gas at room temperature. Can we explain this difference using IMFs and mass? Well, yes, their masses are quite different, so that's probably the largest factor here. In fact, in the entire family of halogens, we can explain their states at room temperature by taking a good look at their masses. We could also say that iodine has stronger IMFs. Even though we're talking about London forces, since these are all nonpolar molecules, remember that London forces are stronger between larger and heavier molecules. So iodine exerts stronger IMFs than chlorine does on other chlorines. Really, when we take mass into account, we're essentially looking at London forces. So if iodine's a solid and chlorine's a gas at room temperature, how do we end up with a state for bromine? We've already seen it in videos. It's an ugly orange-brown liquid. It's a liquid at room temperature, and that makes some sense. It's quite a bit heavier than chlorine and quite a bit lighter than iodine, and so its mass allows it to be a liquid at room temperature.